So this afternoon we will finish with some nice forming limit study. Nice mathematics in it. Sorry about that. Basically, it's mechanics, but you know, mechanics is nothing else than mathematics. There is little physics in it. And what you are doing in material science is actually a lot of chemistry, a lot of also mechanics and even mathematics, all this together. And especially for the modeling, you need a lot of mathematics and physics and mechanics. So this is why you have to develop a multidisciplinary expertise. That should be your... Okay. Yeah. Here. Okay. Thank you. This one too. Yeah. Okay. Thank you. So today we are going to look into forming limit theories, especially the refined consider criterion, Marciniak-Kuczynski model, and the perturbation theory, which is not here, which is actually for the, all this instability analysis started with Consider, who developed that very simple equation for tensile testing. That's called the Consider criterion. That was a long time ago. And then for sheet metal forming, it's more important because many applications are in sheet form. So sheet metal forming, already Hill developed the theory for the negative part of the forming limit diagram, the FLD, long time ago. And then Marciniak-Kuczynski, these Polish researchers, they developed a theory in which an initial defect is assumed, in which finally the deformation is localizing, and then the formability is limited. And much later on, a perturbation theory appeared in 1991, approximately 1990. By two of my colleagues in Metz, and when I joined the laboratory, then I generalized it for the polycrystal case. Also, the Marciniak-Kuczynski theory I developed first time in a polycrystal application. So the Consider criterion is simply when you are looking into the hardening rate of the material during tensile testing. So the derivative of the flow stress, which is modulus, if it is less than the stress level itself, then deformation is localizing, and then sample breaks. So this is a very simple equation, and with the famous researcher Heinz-Peter Stüwe, who was my good friend. He was 20 years older than me, but we were in very good contact and relation. He developed it for crystal plasticity. The Consider criterion in original form, it is for a sample with kind of isotropic distribution in it, but the sample itself can be just a single crystal. And many times we are, we are studying what is the formability of single crystals. And for that purpose, then, if you want to look at as a function of crystal orientation, we use the Taylor factor. So Taylor factor, the M value, is simply I think it's possible to use here, the pointer. Options, the laser pointer here. The Taylor factor is the ratio of the slips, all the crystallographic slips within the crystal divided by the macroscopic strain rate. It can be single slip or can be multiple slip. So if we use this, you see the gamma dot R is really, and epsilon dot and epsilon, they are related. You can put it in, and you can rewrite this instability criterion into this formula. And then here one can distinguish two sides. This is a kind of intrinsic hardening normalized hardening rate, because this is the hardening rate using the resolved shear stress on the slip system. And this is the stress level in the slip system. So this is, hardening rate. Let's call it capital H. And on the other side, there is a kind of geometrical parameter, because M is the ratio of these two strains. It's kind of geometrical quantity without a dimension. And so this formula appears on the other side. This we call instability parameter. The lower this value is, actually the better the stability, because then less intrinsic hardening is needed to satisfy this equation. I mean, this, for the stability, here this is opposite. So deformation is stable if the hardening rate is more than on the right side this instability parameter. So if this is high, then higher intrinsic hardening is needed to maintain the deformation of the whole sample. And if it is smaller, then smaller internal hardening is sufficient, so there is more stability actually. So we are looking for here values which are small. This one is called the intrinsic hardening rate, and the other is the instability parameter. So the considered criterion can be rewritten, but now we go into a single slip here to see the effect of orientation on the stability in tensile testing. So we define the slip system with B and N like this here with two values, key and lambda. And we do so that lambda and B and N and ZY in the same reference, same B and N are in the ZY plane. This one can choose a reference system in such a way the calculation is easier. And then nice mathematics comes. We have to calculate how the orientation change is going to happen for single slip in tensile testing. Well, these formulas, don't worry about to them. This is crystal plasticity, and then you need a basic course to develop and understand these equations. Trust me, they are perfectly correct, and then lead to the value, how much the crystal will rotate in its specific orientation for single slip and in tensile deformation. It's one of the simplest case of crystal plasticity calculation. And then we can calculate how the slip direction is changing, how the normal plane is rotating for the slip. And then we can calculate also the derivative of this m. You obtain the m factor, the Taylor factor, which is basically the reciprocal of the Schmidt factor for single slip.
Yeah. Here omega dot is the rigid body rotation. Omega dot is the rigid body rotation.
Omega dot here is the lattice rotation. Lattice rotation rate, yes, which is the difference between the velocity gradient imposed on the sample and the velocity gradient made by the slip. That's the which is leading to the lattice rotation of. So this is lattice rotation.
Now, say in the next slide, there's a change in the Taylor factor.
Yeah.
Yeah. Now, say suppose like I am starting with the ideal orientation for a given deformation. Then when if the orientation is not changing, the Taylor factor will also not change.
Right. Exactly.
So
for stable orientation, the m value will be constant. So dm d gamma r will be 0. And then if we go back to here, then this is 0 here, and we only have 1 over m. And this is what defines the stability of a stable orientation. Yeah, precisely. But here, what you look at is single slip. So there are a number of experiments for, you can do it, for example, zinc single crystal. If you make it and then you begin to pull, it deforms very high to very large strain in single slip. Not small strain. It goes to strains of 2 or even 2.
But what I couldn't understand is if I have a stable end orientation, then it is giving a highest instability parameter.
Yes, because this is negative here. 1 minus.
Yeah. So anyway, that dm by d gamma is 0.
It's higher instability. This is instability parameter. So if this is high, then you need more intrinsic hardening to have the stability. So it is basically an instability parameter. The higher its value, the more unstable actually your deformation. And during we will see what the simulation calculation shows, that what is happening because of orientation change in single slip and tensile testing, whether it is going to help the stability of the crystal or it will be not helping. That's one of the results what we are going to get now. Okay, so the simulation gives a formula for dm d gamma r. Actually, this is the formula. What we get is a very nice analytical formula, and the whole calculation can be done by hand. There is no need for computer. So lambda is the orientation with respect to the this one, the B, the slip direction, and the Z, the loading. Z is the loading in tensile testing. So this simply the derivative of the Taylor factor is going to be 1 minus tangent whatever square lambda. And then having the m analytically, having the dm d gamma r analytically, then we can actually trace and look at how it is changing. We can even do fully analytically to calculate the orientation of the crystal, the function of strain. So here it is actually, we get the instability parameter in analytical formula. It's only depending on the lambda and the key values, right? So the orientation of the slip with respect to the loading, and then the normal plane with respect to the loading. And continuing the analytical calculation, we have its evolution equation actually as a function of strain. Epsilon is the strain in tensile testing. And the whole calculation is analytical. Now, in this way, we get the instability parameter in which there is going to be, as a function of strain, you see the initial orientation of the slip system. And then this is the strain, that's instability parameter. But one can also make a plot for different crystal systems. You looked at hexagonal, like zinc is hexagonal, and in basal slip, it is deforming very nicely, easily, and then making a lot of deformation. So this instability parameter we plotted here in the inverse pole figure. You see its value is in this part nearly 0.01, but goes very high values when the loading axis is coinciding with the direction of the slip. So here at this position. Here it is infinity actually, and here it is the value is 0 of the instability parameter. For FCC single crystals in single slip, we can plot it also in the unit triangle. So it has not infinite value, it has some value here. It's increment of 0.1, 8, 9, 10, 0, 1.1, 1.2, and lower values are here for tensile testing. Now, considering that in which direction the crystal is rotating, you can see what is the tendency. Is the deformation is going to be more stabilized by the orientation change or not. So for tensile testing in this diagram, grain orientations, they go either here or there. So basically it is decreasing. The instability parameter means that you have better stability. The result is that grain rotation is producing better stability for these single crystals. If you do the whole analysis but numerically for a polycrystal, then you will get this instability parameter for a polycrystal varying, and not too much for a random polycrystal here. You see that for a 0 strain, its value about 0.33, which is basically the reciprocal value of the Taylor factor, you know. And then it is decreasing, but not too much, right? So again here for this FCC polycrystal, you can see because there is a decrease here up to this strain, the evolution of the orientation change is helping stabilizing the more stable deformation. So good news that crystallographic slip is not doesn't make it worse. It is helping the stability of the deformation. Basically, what happens is that the crystal rotates into better orientation for stability. Yes, this point is the classical consider criterion here for isotropic material. So this is showing how in tensile testing an FCC polycrystal in Taylor modeling is going to contribute to the stability of the deformation. Okay. So this is just a kind of introduction for you on a general topic of instability of deformation, and because consider is really very well known, but is not well known this work, what we did with Professor Stüwe, that it can be shown that an intrinsic positive hardening is needed in any case for the stability of the deformation in both cubic and hexagonal crystals in single slip, and when texture forms in tensile testing, It promotes the stability of the deformation process. Now, let's go into the sheet. In the sheet, the Marciniak-Kuczynski model is assuming this groove which is in which the deformation can localize. And when it is localizing, then deformation is stopping outside. So that's the limit. In the theory, it is assumed at a given angle, psi angle, with respect to your reference system. And this is a variable parameter in the theory. So you have to do the calculation for different initial angles of this groove, because the groove angle itself is changing during deformation, except it's not changing in the biaxial case, but otherwise its orientation is slightly changing during strain. But you have to also consider. So this can be done for polycrystal plasticity also, but initially this modeling was done only, kind of isotropic material. The only thing which mattered was the orientation of the groove. What is the defect, initial defect? So the thickness in the groove here with respect to the thickness of the sheet. A small value, almost 1 is assumed, like the thickness ratio here and there, like 0.90, 95, 96. A very small defect is sufficient so that during deformation will localize into that band. So we have to follow the deformation actually in the two zones. In the zone A, which is the matrix in the big sheet, and the zone B, which is the groove. We write some basic equations. The compatibility equation, the main compatibility equation is that the strain component in direction 2 in the groove, epsilon 2 to B, has to be equal to the strain in the matrix. The groove keeps its length. That's a constraint. It is always within the sheet. The other is the equilibrium equation, so that the forces are transmitted across between the left and right part of the groove. From left and right to left, the forces are transmitted through the groove. So when you calculate the force, for example, in direction 1 in the groove, and this is the stress component multiplied with the thickness, it has to be the same in the matrix zone. And this also the shear component is transmitting the shear stress. If there is shear stress, and of course there is, because forces are working in different directions, there is sigma 1, 2. We are in the groove reference system here, you see. This is also transmitting from one zone to the other, the force itself. So these are simple equations, but they have to be satisfied. We have three equations, one for the strain and two for the stresses. We are in a plane stress state in sheet forming. So the stress components, which are possibly non-zero, they are here. And then the zero stress components are here. We have hydrostatic stress and also the deviatoric stress. The total of the deviatoric stress plus hydrostatic stress is making the true stress, sigma j. And applying this equation on this component, one finds immediately that the hydrostatic stress value is equal to minus S33, where S is the deviatoric stress tensor. So finally, this is the total stress tensor for plane straight state. Here, the deviatoric stress is appearing, and in crystal plasticity, if you don't have elasticity, only plasticity, this is what we have. We only have the deviatoric stress. We don't have the sigma stress state immediately. But with this boundary condition, as you can see for sheet, we do have the hydrostatic stress value, how much it is right here. Then hardening has to be included in the simulation. The hardening here I'm reporting about a work which was done, well, actually 30 years ago. This is when the first time we introduced the polycrystal plasticity into the forming limit diagram. The principles are still the same. Here we were detaching, decoupling the hardening into two parts. One was tau C, so that the increase of the stress state, the deviatoric stress in the material, is a multiplication of this tau C value and a constant stress value, which is related to the texture state of the material, and tau C is related to the hardening state of the material. So we somehow decouple them. For the intrinsic hardening, we use this extended Holomon type equation here. Then we have an exponent and an m here, and then tau C0 is the starting strength of the material. Since then, this hardening law, we can do better actually. What I presented on Monday, and we do the exercise on Tuesday, can be applied in a similar way, and then more general can be obtained. This was done at that time. So then our equilibrium equation for the two equations for the two stress transmission of the two forces through the groove can be written in this way. H is the thickness in zone A. HB is the thickness in the groove, HB. And these are the stress states due to the texture here and due to the hardening of the material. So these equations are to be solved. What is unknown is HB. How HB is going to change during the strain. We have an initial state for the thickness, and it's going to be decreasing. So the HB over HA ratio will be decreasing. This is how deformation is localizing. We have to find out what is the stress state in both regions, and then satisfying these equations, we will get how the thickness within the groove is reducing. So to get the stress states in the two zones, we use polycrystal plasticity. Yes, using the yield surface and compatibility, right. But now let's go into the strain parts. What is happening during this Marcheniak theory is this is a presentation of the so-called minor strain in FLD and major strain. For the positive part, and also for the negative anyway, plane strain state is approached within the groove. So we impose in the simulation a constant strain path, you see, that we just deform the material imposed on the sheet. So the sheet, the state in the region A is moving on this line, and region B, we obtain the solution, how the deformation is going on. Deformation is deviating already from the beginning slightly, and then it's increasing. At a given large strain within the groove, the deformation is deviating so much that it becomes plane strain, so that only the major strain is developing and the minor strain is zero. The groove is decreasing its thickness. Its length is the same, but actually with the thickness also there is change in its dimension, the width dimension. That's the other component. That's plane strain. So to detect the occurrence of the instability, so at which point we have then end of formability, is you look at this situation. So if it is approaching the plane strain state, so that is moving up the strain path within the groove, then there we are. This point in the region A will show us where is the end of the deformation. From this point on, the phase A, the matrix, is not deforming anymore. Only the deformation is happening inside the groove. So this is how it is looked at, and the decision is made. And now a small increase in strain here, you see, enormous increase in the groove, so it's localized. The rho is the ratio of the two strain rate components, which defines the strain path within the sheet. Okay, so here's some results. Here aluminum sheets were deformed with 3 different initial textures. Here I show the textures. See, it's a kind of fiber and kind of quite strong cube component is there. Here the cube component is weak in this texture, and here it's again, it's like 90-degree rotated version of this one. Okay, and the hardening, it was simulated. As I said at that time, using this Holloman type of equation, the simulation is not that perfect. Since then we are doing much better, but this was the fitting at that time. Now, the yield surfaces were calculated to show, because basically what is happening that the stress state is moving on the yield surface. So, for example, biaxial deformation, we start here for the sheet and also for the groove, but for the sheet it is going to move in this way by hardening, but in the groove the stress state is moving down into the plane strain state, and when it is reaching that position, then deformation is fully localizing in the groove. So here, 30 years ago, the Taylor model was used, rate insensitive slip, 700 grains, and then this was assumed for the slip families in aluminum. So here we have the results, the predicted results here are shown when texture evolution is not considered and no variation in the groove angle here. Then this kind of prediction is coming. It's like the old calculation in which you don't consider texture evolution. At least the texture itself was considered. So there is effect texture A, B, and C, they lead to different, very different FLDs. You see, very different. So, for example, the B texture, which is not a cubic, has the lowest formability, and the A and C, which contain the larger cube component, they had much better formabilities in sheet metal forming. So the texture dependence is very, very high on the positive part of the FLD, but very small in the negative part, you see, the prediction. Now, but if we vary the groove angle, it has to be varied because, you know, we have to find the minimum strain in formability. Smaller strain at which there is already instability, you know, it doesn't permit to develop other strain mode. So here you see big changes happening. A, B, C, and textures. Now the B texture has the best formability, and the A and C, but we have the cube component, went down. But here there is no texture evolution, only we varied the groove angle. We have to do both, so we have to update the texture evolution, and then also vary the groove angle. So here we are varying now the groove angle, okay? Without texture evolution, this is what we already shown, and with texture evolution, this is the predicted result. It seems to be that the negative part is almost identical, texture independent. Positive part, it's almost the same here, and there are some differences near the biaxial only. So it's interesting that there is this kind of uniform behavior, and only this biaxial part is texture affected and groove angle affected. Yeah. There are some changes in the texture during this strain. Strains are not too high because it's like the value is how much we go up to 0.3 here, yeah, and 0.3 in the other. It's relatively not too big strain in sheet metal forming. And then also for the negative part. Tensile testing is somewhere here. But this tensile testing is actually, it's a line here. It's not plotted, but more or less this line. Yes. So there is evolution in the texture, you see. So this texture goes into this one into this one, and so significant changes are happening in the textures. There was a possibility to compare the texture evolution with hydraulic bulging, which is equibiaxial tension, and here the initial texture was of this kind, and the measured texture, deformation texture, was this one, predicted, and I don't know if there's comparison. No comparison. Sorry, there is no experimental value here. I don't know why there is no experimental value. That's too bad. There's no any measurement for FLDs. Are you doing FLD measurements here? Yeah? I was doing for titanium in Belgium, in Leuven. Very detailed forming limit measurements were done. Now, let me speak about this. This is really important, the texture effect, so the polycrystal effect on the critical groove angle in this theory. On the left part, here developed, for the left part of the FLD, that simply the critical groove angle is arcus tangent minus square root of minus rho. This is the Hill solution here. He also suggested that for the positive part, it is 0. So the minimum strain you get when the groove angle is 0. Well, the polycrystal simulations confirmed very well the Hill prediction. So his theory is good for the negative part. And concerning the positive, which is starting here, where it is 0, yes, but not everywhere. After a certain in a certain strain path in the in this approaching the equibiaxialis here, there is strong texture dependent for the groove angle. So the polycrystal simulations confirmed Hill's theory for the negative part and did not confirm his theory for the positive part. We can look at the evolution of the yield locus, the yield surface also during deformation. So here we see the A, B, and C, the three materials. So the yield surfaces, yield functions are plotted here. And there are changes, but not very dramatic changes in the shapes of the yield surfaces, because basically the strains are not that much. So in the shape, not really much is expected to change. So these are the conclusions on the Marchniak-Kuzinski theory, that forming limit depends on the initial texture. In the positive part of FRD, the negative is basically independent. The critical groove angle is not 0 in the positive part, opposing to the Hill's theory. And the effect of the evolution of the deformation texture is kind of equalization of the FRD curves. So this was an old work, it was a long time ago. But after we had another history with the forming limits, because my colleagues were working on this one, and then they developed the so-called perturbation theory. That I liked a little bit better. So I'm going to continue with that one. This is more general, I believe, and different from this initial defect theory, because here the defect will be assumed not only for the thickness variation, but for all the parameters which are in the process. Much more general. So the first work, establishing the theory itself, was done by Tuzinski and Molinari in 1991. And then when I arrived to the lab there, then we developed in 1996 how does it work with the polycrystal plasticity and strain path dependent hardening, so in the most general case. Now, here the theory is quite substantial. Many more equations are appearing. A lot of mathematics in it. It's logical because we are going to do perturbation on all the solution of the so-called homogeneous solution, and to see what is happening. Now we are doing polycrystal plasticity, and in polycrystal plasticity we have a good code. It can be a Taylor polycrystal code, it can be the VPSC code, which is capable for you to provide the stress tensor, the whole stress tensor for a given strain rate, what you impose. And then you update the strain, and then you can have the evolution, and you have the evolution of the stress state, and so on. But this is the basic thing what we need from the polycrystal. So we impose a certain strain rate, and what is the response of the polycrystal. Now, here we are in polycrystal viscoplasticity, and in viscoplasticity, what's happening that this kind of yield surface, kind of unique yield surface, is not existing. There is no critical yield surface in viscoplasticity because at any level of stress there can be strain rate. So there is no critical stress for which, below which there would be no strain rate, and when you reach that one, then there will be strain rate. So the viscoplasticity a little bit different from the rate-independent behavior of materials. This is a little bit complicating the situation, but we found out that let's not use the yield surface because it doesn't exist, not use it, but we defined so-called yield potentials, which are replacing the role of the yield surface. A yield potential is defined with the help not only the stress but also the strain rate, because a yield surface in independent plasticity is independent on D, the strain rate. You only have the sigma, and you can make your plasticity criterion only with the stresses. No need the strain rate. But when you have viscoplasticity, they are combined with each other. So we define a yield potential function, and by multiplying the two, multiplying the stress and the strain rate. This is the actual, no need for the dot actually, this is already strain rate. When we multiply with contracted product, then this is just basically the plastic work, or with rate, strain rate, it is the plastic power. So the plastic power should be constant along the yield potential. The plastic power. The plastic power in general is multiplying the stress with the strain rate. In the polycrystal stress, polycrystal strain rate. It should be constant, so we choose a reference value, which is a given sigma 0, D0 combination. This is the reference value. So all along of here, you see there are two different yield potentials shown here. They are similar in shape if there is isotropic behavior. Anyway, they are similar in shape if we only change the strain rate. But what is happening that if we are at a given, let me see here, if we are at a given stress level sigma prime, by increasing the strain rate, we are going to jump on another yield potential. These are equipotential functions, and they are defined like this. So the plastic power is constant along. Now, the complication is that for a forming limit diagram, perturbation theory, we still need the yield surface because we would like to approximate in this perturbation theory. We need to put it fully analytical so that we can apply our perturbation equation on all the material behavior and everything. So there is no use for a non-analytical yield surface or yield potential. So we are going to fit locally the yield potential with an ellipsoid, so-called Hill ellipsoid. So this is why we need to really to define well the so-called yield potential function. Now here we can use the help from work of Hutchinson 1976, who wrote a very nice paper on viscoplasticity for polycrystals, and then he showed that if we have a d dot stress strain rate to which there belongs sigma stress, and if now we increase the d dot lambda times, so we increase the strain rate lambda times, then the stress level will be increasing lambda on the power of m times. This is a nice, simple, small relation between two equipotential surfaces. Like here, this one and this one. So if we apply this relation for these two states, we can link the two together by defining, a reference value, and then we get simple transformation formulas. How can we jump from one yield potential to the reference one? We must stay on a reference one, and it has to be guaranteed. So this is why this was developed for this specific application of viscoplasticity for for the perturbation theory. Now we can make sure that really we are on one single potential. We are going to fit locally that general yield surface at the point where we are loading the material with an ellipsoid locally. Of course, we only use very, very locally. So we use the Hill ellipsoid. The Hill ellipsoid is very suitable because it has, this F, G, H, L, M, N coefficients, which describe the yield surface of the Hill yield surface. Here, this is used for potential, but whatever, this is an ellipsoid. We just have to find what are these parameter values, and then we have a good analytical description locally at the loading point for our purposes to do the perturbation theory on the stress state and on all these parameters. In sheet metal forming, there is no 6, but only 4 Hill parameters. So there is the F, G, H, and the N parameters. In this format, we define the yield potential, so that the F sigma, which is the yield potential function, we divide its value by the reference value, and then we get the so-called Hill ellipsoid, which is going to be equal to 1. So it's the normalization. This is the equation which is relevant here. But it is done in such a way that the previous, this sigma 0 d0 condition here is satisfied that whatever stress state we obtained in polycrystal simulation, we are going to put it on, jump it on the equipotential, yield potential on our reference one. To fit polycrystal yield surface, we need to fit with the ellipsoid, we need 4 stress points in the vicinity of the loading point. And then those 4 stress points will produce then 4 relations here in which the unknown is FGH and N. So these 4 stress points are calculated with the polycrystal code near the loading point, and then this fitting is done. This requires a small, program. Here is an example how this is working. So the yield surface, its positive part for sigma x is shown here, not the whole yield surface. The continuous black line, first the initial one, which is the dotted line broken line here. This is the yield surface of the initial state. Okay, and then we deform the material in equibiaxial stretching. So this is our loading point. It is going to move into this point here. Oh, I lost my pointer. Okay, so this is the loading point, which is moving into that point after a strain of 0.5 logarithmic strain. Strain rate sensitivity is 0.01, small, but still we have to do the correction for the yield potential to make it very precise. So this is aluminium material, and this is a like kind of concrete example. You see how one can nicely fit this locally with an ellipsoid. Ellipsoid is very much elongated. It's not necessarily at 45 degree, because this is a textured material, anisotropic. It would be actually at the 45 degree, the ellipsoid, if it would be an isotropic material. Now, after deformation, we trace, here you see, we trace just for showing the polycrystal yield surface, yield potential, not yield surface, yield potential, and the fit with the Hill ellipsoid. You see a lot of changes happening in the shape and the size of the fit. And now, then this is going to be, our yield surface. We only need it locally, and then we can use it. We can use the normality rule, associated flow rule, to link the stress state to the strain rate state. So that provides us a lot of equation which permits to solve the homogeneous solution problem when there is not yet instability. And then we are going to make a perturbation on that. And here this is another strain path. Here the rho is 0. So here we are already in the loading point. Rho equals 0 is, when in the FRD you go straight up at that point. The first point is a plane strain point. If you load it that way, then the loading is at this point on the yield surface, and it's not moving basically. That's interesting that, here that strain up was applied 0.5, but it was not moving significantly. And then there is a lot of change in the Hill ellipsoid. It is tangent before and after. It becomes more flat, the yield surface, as we apply the strain in the rho 0 equals 0 position. Now, strain path dependent hardening was imposed here. This is the rho defining the strain path. Equivalent strain rate was the von Mises strain rate. The equivalent stress was not von Mises, as I explained you before already. For an isotropic material, you cannot use the von Mises equivalent stress formula. You have to use the so-called work conjugate equivalent stress, which is obtained by, here you imagine that epsilon dot is on the left side. So epsilon dot times sigma is a plastic work. On the other side, component by component, you calculate the plastic work. The two has to be equal. And that, once you define the epsilon dot equivalent, and we accepted the von Mises one, then this formula gives you the value of the work equivalent stress. In that work, what I'm presenting, polynomial fitting of the strain hardening curve was used in order to have analytical formula. As I said, everything has to be analytically written so that the mathematical perturbation theory can be applied on it. The one is the hardening. So we fitted with a polynomial where the Ci are the coefficients of the polynomial and the epsilon I, here is the, the exponent. So for a number of about 50 or 20 coefficients, when you use, they describe very precisely. It's a simply mathematical description of any curve. At least this kind of string hardening curves with polynomial fitting work very nicely. If you compare this with the usual power law holonom type of function, you see there's a big difference. Here there's just one single n exponent, while here there are, 1, 2, 3, 4, these integer number exponents, many of them, and there's several Ci parameters, of course. But one can compare that actually if one considers using using this formula, but with n variable here, and n is n star. If n star is varying using this formula, then actually you can use this formula for the perturbation, but you have to consider that n is variable. So this is how we actually did at that time. This can be managed differently as one would like to do, but then if it is changed, then the perturbation theory equations, that part which is related to the hardening has to be updated. And then this part in the crystal plasticity simulation, you have this constitutive law with the strain rate sensitivity, which is relating the local shear stress to the slip system to the slip rate. We have self and latent hardening, sophisticated one, with this hardening matrix, so that the slip in all the slip systems, they produce increments in the strength of the slip systems. And then this hardening matrix is controlled by 4 parameters, H0, tau sat, and A. And further, there are these self and latent hardening parameters, which are put into 4 categories. So basically, there are 4 parameters here. This is a very sophisticated, as we showed, very good agreement with this. If you use somebody is using this in polycrystal plasticity, surprisingly good agreements can be obtained with the macroscopic curves. Here is a demonstration. So here this is a real tensile testing of aluminum, magnesium, silicium material in tensile testing in RD and then TD direction. And you can see that if one follows the procedure, polycrystal plasticity is just reproducing fully, perfectly the macroscopic observed. Of course, there are parameters in it. There are a number of parameters. Here they are. You see, there are, of course. But the result is quite spectacular. We have the 4 self and latent hardening parameters. We have initial strength of the material. Tau sat is the material tau sat, and then the rate hardening, this one, and then the A parameter. That's it. And it is just reproducing perfectly. Once these parameters are obtained, that's a separate exercise. Then they are used in the polycrystal model for all the other strain paths, hoping that it's also valid for all strain paths. The result will be that you will have a strain path dependent hardening curve. It's not going, you're not going to have one single curve for all deformation mode with equivalent stress and strain, of course, but they will be depending on the strain path. Here is the simulation, which shows the minus 0.5 is the tensile testing, on which it was perfectly reproduced. And then if you plot it for the other strain modes, this is when rho is 1, equibiaxial stretching. And this is 0.5, it is between the plane strain and the equibiaxial. It depends on the strain path. It comes naturally by the simulation. And then, as I said, for simplicity, if we use this in the perturbation theory, then n star is going to be a variable with strain. This is just to show how it varies. Now let's go into the mechanics of the perturbation technique. Or should we make a pause, a break, because it's horrifying, all these equations you will see. So it's better to be well prepared. Yes, let's make a break, yeah? 10 minutes or so that we can have some more energy to see these equations, okay? 10 minutes. Sam, what do you have? Did you make progress?
Yeah. I don't know code and I don't
Oh, what is this?
morning my
Oh, okay.
I don't know code. I'm getting till this point.
Oh, good.
But I want this intensity now and just completely
Yeah. So you have tuning here, yeah? No. I hear you don't have tuning. No tuning.
and I want more intensity.
Hexagonal.
As of now I'm using 300 degree.
Oh, you have a large string.
Yeah.
Show me the control file. I think you have a two large string and
I want to change the parameters now. I'm just changing the parameters.
300 times 0.01 is equal to 3. 3.0. You have a string of 3.
Actually I tried 1.6. Actually it came around 1.6.
No, see that you cannot keep changing.
No.
Strain you cannot
Strain is your
based on the experimental, like how much total
How much
information
it is?
you
How
have
much
given.
it is?
This you cannot vary.
No.
I tried if I increase more strain only I'm getting that.
No.
No,
That is wrong.
No, that is no. This is not variable.
Yeah.
Then I can take as 1.5.
Not 1 as 1 point.
What is
yes,
that?
even like 80% thickness reduction. Okay, that 80%
I
thickness
calculated
reduction that you have to calculate the increment stress.
Yeah.
I calculated and I got around 1.7.
Yeah, that is
So
80%, then 1.7, yeah.
so
I think with 1.7 it is going to make that component, yeah.
so I tried with 1.7, but I'm not getting.
Right, no. No. Also here, try to put it 0, okay, for the moment, so that you keep the grain shape. Let's just see how much the effect of the grain shape. Can you do a simulation for 0? And show me after, okay? But you go back to the string.
This is 1.7.
That's not reasonable. Okay?
So you can have a coffee.
Oh, there's coffee?
Yes.
Good.